Sequences and series. Here's what happens. You have two things here. Sequences, what we're going to look at, are basically a set of numbers with commas. One after another, one after another, one after another. Excuse me. We're going to be finding patterns within the sequences. We're going to be able to write out a rule for the sequence. We're going to sit there and we're going to write out the difference between a finite and an infinite sequence. And then we're also going to talk about what are called series today as well. Correct. And how can you tell the difference between finite and infinite? Yeah. You guys know what dot, dot, dot means, right? Infinite, infinite.
Ad infinitum.
Yeah. That's really all it is.
That confused me.
As you start to go through these things here, what we're going to do here is there's no reason for us to write down all this mumbo jumbo, but just to kind of go over some of the actual terms that you're going to look at. Sequence is just a set of values. Again, the domain are how many are there in the sequence? Well, there's 5 numbers here in the sequence, so the domain would be 5. The range, well, what are the differences in the values? Well, it goes from 3. It's just the numbers in the sequence. Have we? You might have done a little bit of this. You're trying to find, you've done pattern recognition, and that's kind of what this is. We're just going to start talking about, we're going to be writing out the rules for the patterns.
So it's like doing the input box and what you find.
Yeah, that's basically it. I mean, for this one here, 3, 6, 9, 12, 15, what's the pattern?
+3.
Now, if you do plus 3, that means you're starting out with 3
So
plus
y
3.
equals 3x.
X plus 3? What?
3x plus 3. No, yeah.
Okay, so
No. Unless if x is x starting at 0 or 1?
we start with, well, it depends on how you write out the rule. And that's where things get muddy. What you were saying there, Russ, it was like, it's 3 times something. You've got the first term, second term, third term, 3 times 1, 3 times 2, 3 times 3, 3 times 4. When you guys are saying plus 3, okay, that's fine. You can do that as well. Well, it's starting with 3 plus 3, and then you have to write out a rule to be used with addition. A lot of times it's easier to write rules in multiplication. Because multiplication is repeated addition. See what I'm saying? You're right in thinking that it's just plus 3, but that's just kind of one of those things how it goes through. No. As we go through these, what I want to do here is kind of show you how the patterns work. Again, this is not anything that's going to be horribly scary bad. If they say write out the first 6 terms, well, that means we're going to start at 1. So you start with your value of n for the number. This subscript, a sub n, this n value is the number term. So a sub 1 would be the first term, 2 times 1. A sub 2, 2 times 2. A sub 6. Again, this is nothing scary. Yes, sir.
After you get that first one, can't you just keep adding?
2.
Yeah. You don't have to plug it all in.
No. And most of the time, can't you just use your calculator and go to y equals?
And an instance like this,
Correct. But is it something that you can do if your pattern gets weird? But you understand what I mean by saying y equals? Because this is just input, output. That's all it is. Yes, sir.
Do you have to start at like a sub 1?
Yeah, this will be first term. There's going to be slight rules as you get into this. When we get into the series, you'll see why. They will specify it. But for sequence, that's your first term and second term. You don't have a 0 term.
Or maybe this term?
Correct. Again, this is nothing going to be scary. It's just a matter of starting at 1, going through 6. What are the answers? Boom. I'm not going to waste my time. Writing rules. This is where things get interesting. Trying to decide what your rules will be. Now, again, one of the things you'll notice is that, let's look at the first one. Let's move it on its own sheet. We're going to write a rule for the nth term. The nth term is your general rule. That a sub n. How do you get to that one? So when you start with something like this, we have your first term, second term, third term, fourth term. What I want you to recognize, do you see how the fractions are changing signs? How do you change signs in math? Multiply by negatives, okay? Because that's how you can be able to alternate between positives and negative values. It could be. You can work through them via exponents, you can work through them a different way. It's just kind of dependent upon how you set it up. So in this case, if I want to write out in terms of n, where n is if I let n be the first term, how did I go from negative 1/3 to 1/9? What did you do to the negative 1/3? You multiplied it by negative 1/3. Okay. How do you go from 1/9 to negative 1/27? Okay, so what are you changing?
Almost calling it, so you y equals
1/3 x.
No, because
No,
you're using the previous number.
Because exactly, you're reusing that previous number. So if you start writing it out like you're saying, that means that x value would be your n, I'll use that as n. If you're saying that's n, well then it would be negative 1/3 times 1, negative 1/3 times 2, negative 1/3 times 3, and so on and so forth.
But it's dividing, so you would have to put 1 over.
Well, even if I do that, if I'm doing that 1 over n,
Well, 3n.
oh, okay, you're saying that?
Yeah, and then it's going by 3, it's just going by multiples of 3s.
So, but how do you denote that the n is going by 3s?
Because it's 3 to 9, and 3 times 1, and it's 3 times 3, and there's 9 times.
Okay.
3. But it's still going to go.
Now, hold on a second here. This is, when we're starting with this n value, n's going to change from 1, 2, 3, 4, and so on, okay? So if n is 1, you get negative 1/3 times 1/3 gives you, that would be negative 1 now. So the way that your pattern is saying won't work. Correct. In order for this pattern to work correctly, it's the exponent, bless you. It's the exponent. You start to play around with different values. Sometimes it's not the multiplying, sometimes it's the exponent to make it work. Because if you think about it, whenever you have even exponents, don't they become positive? Odd exponents can be negative. So as n becomes 1, if n is 1, you have negative 1/3 to the first power, negative 1/3 squared, negative 1/3 cubed, and so on and so forth. That's how that's going to work it through. So you might have done pattern recognition before where it wasn't so fancy, shall we say. But in these cases, you might have to work a little bit further. Use your calculator, plug and chug, go through a couple of things, try to get to it. Some of these are going to make you mad. Oh, I didn't think of it. Okay? Because that's what they do. All right? That's what they do. Same idea here. 2, 6, 12, 20. 2, 6, 12, 20. Think of it in terms of first term, second term, third term. I want to get it into some generic rule. How am I going 2, 6, 12, 20?
Could you have multiple n's in one?
Yes, you can. Yes, you can. Yes, you can. Go on, say it. I think you might have it.
N plus n.
Oh, you're on the right track.
N plus 2.
No.
Just joking.
Now, again, think of it in terms of first term, second term, things like that. How do you get, more often than not with these, there probably is some multiplying one. How do you get 2?
Well, you have to multiply 2 times 1.
Okay,
So it's
so 2 is 1 times 2. What's 6?
2 times 3. 2
What's-
times 6.
What's another one? 2 times 4. What's the next one? Now do you see a pattern? What's your first term?
1,
1. What's this one? 1 plus 1.
1,
2. 2 plus 1. So what you're doing here is take your first term, multiply it by that term, plus 1. It's a giant puzzle that Brenda doesn't like. Okay? Again, think about what's going on here. If your first term is 1, that means it's 1 times 1 plus 1. If it's 2, it's 2 times 2 plus 1, and so on. It's weird that you have to start to think of that, but it's completely different than anything else we've done this entire school year. I know. Okay? It takes a little getting used to. All right? Those. Now, the difference that we can have are series. The series is when we throw in the addition symbol. The difference between a sequence and a series is that the sequence is just a list. A series has the addition. Okay? So the main difference there is that you throw in the addition between the terms. You're adding up all of your terms. So if you wanted to figure out what 3 plus 6 plus 9 plus 12 plus 15 is, well, how many terms are in that series? 5. There's 5 terms in that series. Do you remember what the pattern was for that one? 3n. So what happens here is that we can write this in what's called sigma notation, summation. You guys have seen the summation symbol before, right? That funky E.
Yeah.
Not usually. It's Greek letter. Sigma means summation. You use this for series. You're adding up all the terms in a series that start at the first term. We say where you start at your first term, n equals 1. Goes on the bottom. That's the first term you're starting at. How many terms are in the sequence in this case? There's 5 of them, so we put a 5 up here. And then what was our pattern for this one? It was 3n, wasn't it? And that's what that looks like. That basically means take 3 times n for 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, and add them all together. Oh, really?
Yeah, and now,
Now you're wiser. Yes, sir.
So since that one on the left has 5, the one on the right has ... What would you put for the top?
Okay, correct. That's exactly right. This is an infinite series. So being on the top here with this ... since I don't know how many terms there are in the sequence, or excuse me, in the series, I still use my summation symbol. I start at my first term, my pattern is 3n, and I go to infinity. Beyond that, I don't know what to do.
Does anyone actually mean? Wait, what? How is that from?
Infinity is
Infinity,
beyond
I don't know what to do.
that.
You can't do that.
I was doing an infinity beyond joke, like to infinity and beyond.
But like,
Buzz Lightyear.
I thought it was a math joke, but I found it funny.
Okay. I'm really not funny. So, what's nice though,
Has anyone actually reached it?
did they cut it a little too short? Take a little brain power out. Now, this is where you guys are going to really like me. Take your calculator out real quick.
isn't there an E button?
There's an E button.
Yeah,
The sigma?
I don't know how it works, but I couldn't.
Now you know.
I was just typing in random things.
Yeah, then no good. There's infinity.
Oh, let's see, I forget which one was underneath. I think it's under math.
It's
Found it.
if you go alpha window.
Yeah.
2.
Yes, thank you. Alpha, window, 2.
Oh.
You get sigma notation. Well, here's what we're gonna do. Our calculators, I mean, yes, you could type in n, but use x. So if I want to type this in, hit x equals 1, because we started our first term. We went through 5, and it was 3x was our pattern. Dun dun dun.
Well, simple.
It'll do series for you. It does summations. Calculator will do summations. You don't have to go through and type it all in or write it all out. Because adding, I know, can be difficult sometimes for us.
Is there a way to put infinity?
No, there is no infinite. There are rules when we're doing summations of infinite series. We will get to that. There are rules and formulas to solve that.
Would the answer be infinite?
No, actually, what happens is they're adding to a certain value, and there's a value. We will talk about infinite series 11.3, I think. I don't remember what section it is, but we do talk about how do we work with them. Arithmetic, geometric. Oh, I'm sorry. We talk about infinite geometric series in 11.4. There are some rules for that, and we'll talk about how you can add approaching a value later. There's time for it. Okay. What's arithmetic sequence? You've done this. What's the difference between arithmetic or geometric series? One's adding, one's multiplying. Just like you had arithmetic and geometric stuff in geometry. No? I remember it. Again, just writes it all out. Their book uses the value I here. Don't worry, it doesn't mean imaginary, just they're using it as a variable. I don't know why they use I. It makes no sense to me. So let's write out summation with these two. See if you can figure out the patterns of what's going on. Sometimes it's easier to figure out the pattern first prior to writing it out in summation notation, because then way you can figure out some of the bits. Got the pattern for the first one here.
Yeah.
We didn't know.
Second one was easier.
All right, so here's the deal. I'm not going to lie to you. My E's get really lazy. All right, fine. I will go slower.
Just write it in here. Like when you know what it means.
How many terms are in that series? 20 of them. Everybody figured that out? Okay. And what was your rule?
5x.
What was the sum of that? You guys?
It was 1,050.
How much?
1,050.
1050? I thought you were saying 10,000 for a second. Like, oh, really? 1050. Okay. All right, now on the other one. What is, it's a never-ending one, so that means your top value for this sum is going to be infinity. N over n plus 1. Good. Very straightforward. Now, I used n that time. The other time before I used an x. Does it matter which one you use? No, it really doesn't.
You know what it means.
As long as you use the same variable.
Although we should probably not use
Yeah, like I said, I don't know why they use on. They're just kind of silly. All right, we did this one. This one's easy. We did that one. Blah blah blah. Okay, what do you think you have to do here?
Let's find out
Okay.
what it means.
Okay, what do you think you have to do here?
calculator.
Put that in your calculator. See what you get when you have a square term. Does it change anything up when you type that in? What was it? Alpha window 2. That's how you get to summation.
Can you subtract that
Can
one?
we see the thing?
Alpha window.
You didn't write it down that fast? Jeez.
We're so late.
I'm joking.
What? Alpha window.
Alpha window number 2. See how they started this one at 3?
Put it out like crap. We're doing shit.
Maybe we should get some H's and K's with this.
Yeah.
Yes, it's that easy.
I got 94.
Did you guys?
I got 103.
I got 94.
What did you use as your starting value? Oh, thank you. See, and you asked me about that question earlier. Are they always going to have that? So I'm glad you were the one that made that mistake. It's a learning moment. Amateur hour, yes. All right. You okay?
Yeah, just the interaction with Jason's.
Interesting?
Yeah.
To say the least. Just not in smile.
Okay.
So long before this book was written, I just wanted to show you these. I should say, long before you guys had calculators in your hands, there were actually formulas that you had to memorize for special patterns for summation problems. So you would have to go through and multiply stuff together and do some of this junk. Well, this is just kind of pointless now because what can you do in your calculator?
Just
Solve.
So here's what we do with these formulas.
That's
What if you don't have a calculator on?
Like cow.
Then you'll be multiplying. Oh yeah. Oh yeah. Then we'll have to let Tom. He'll have to memorize those.
Really?
Mm-hmm.
Yeah.
That suck.
Yes, it will. Because I mean, it's not that bad. It's just kind of annoying.
I'm surprised you didn't make this one with equations first.
Right.
And show us.
I mean, really, in order to do this one here, all you have to do is take 35 times 36 times 71 and divide it by 6.
Still kind of
Just multiply it out.
That's still
A lot of work, but you can do it. I mean, it's not terrible.
no.
Tom's benefiting
You're right. Tom's knowledge base now is just going to supersede all of ours. He's going to be a far better off person for it.
He watches this video.
I do too. We should all say hi to Tom.
Hi, Tom.
Hi.
You said say hi.
Hey,
Has to be in the most obnoxious way possible.
do those. Pay close attention to the ones you have to write, figure out the value for the rule, the a sub n. That's going to be the trickiest stuff for you guys to find the patterns. If you don't find all the patterns, it's not the end of the world.
As you
It takes a little while to figure them out. Okay? Yes, sir.
Is the odd applying to both terms?
Yes, sir.
Just the
Yeah, that way you can check them, because I know that some of these values can get kind of
Well, I
funky.
do, but